electric pencil sharpener at DfM. Overall product goal is an electric pencil sharpener whose goal is to sharpen a pencil automatically. It's made of a sheet metal blade assembly. The body of the sharpener is made from injection molded plastic and is constructed primarily via manual assembly. Here's the blown out CAD. Primary customers are school districts and office buildings. We expect this to be about 100,000 units annually. Our secondary customers are private customers for use within a home or an office. This is about 10,000 units annually. Here's our fast diagram.
Here we have two fishbone diagrams showing two assembly sequences. The first one assembles the bottom part first and then the top, while the second one does the opposite. Here you can see that we compared both sequences and found that sequence 1 was ideal. And here's our function component mapping matrix showing the function of each piece of the pencil sharpener.
I will now discuss the cost estimation of each of our parts. Here we have a bill of materials which lists all 17 parts along with their quantity, manufacturing and assembly processes, as well as the material and individual cost of each of these parts. The total cost comes out to $12.69. Here we have our quad chart, and it's important to note items of low functional importance and high manufacturing costs, and in this case the sharpener main body fulfills this criteria.
Here is the functional differentiation table dividing the different functives of the product. The only functives that differ between the customer groups are preventing injury and minimizing noise. Next is the component commonality table showing which platforms remain constant between variants, and the main sharpener body, which is modular.
The sharpener main body is our modular component for the secondary customer group. At-home users will most likely be placing their sharpener on a work surface, so integrating utensil storage increases footprint efficiency. Additionally, offering the sharpener in multiple colors will help it blend into a user's home space. When comparing the secondary module to the primary, the only difference is this modular component, which will require different tooling to include the molded utensil cups. Since the interface of the modules is not changing, there is no difference when compared to the original design. Both modules use a snap fit to fasten the body to the sharpener container and the sharpener lower body. Here you can see the assembly sequence chosen from slide 8. The sharpener main body is the only modular component, so it causes the assembly diagram to split into two paths. Using delayed differentiation, the sharpener body can be assembled as the second to last step to reduce the number of stages that require two paths by one stage. Here we have the design for manual assembly. Here's the assembly time for each component broken down to its handling time and insertion time, with a total assembly time of 139.71 seconds. Based off the total assembly time, the theoretical minimum number of parts is 9. The manual assembly efficiency is 19.3%. Based off of this, the two components selected to be redesigned is the sharpener lower body, because reducing its fasteners will result in an overall decrease in assembly time. This choice is validated by the quad chart, and also the proposed changes won't have any effect on its function. The sharpener main body is the second component chosen, as it has a relatively high handling time and is the only modular component. This choice is also validated by the quad chart, and these proposed changes won't have any effect on its function. Here you can see the snap fits were added to the top of the bosses to reduce fasteners. Semicircle lips were also added to improve the ease of insertion. A swept notch was also included to facilitate its orientation to the sharpener main body. The fastener bosses here were modified to accept the snap fits from the sharpener lower body. An extrusion was also added to the rear fastener boss to increase ease of insertion and eliminate nesting. This has the largest impact on handling time for the part. Lastly, the lip was added to facilitate its orientation to the sharpener lower body. Here you can see the updated assembly times based off the redesign, with a new total assembly time of 122.56 seconds. This reduction in assembly time is success. The number of theoretical minimum number of parts is the same, which results in an increase in efficiency to 22%. These redesigns have no effect on product function. However, there's a negative effect on manufacturing costs because tooling complexity will have to increase.
Here's our design for automated assembly. Our components for the blade, primarily the blade casing assembly. This justification was the assembly has a high cost and importance on the quad chart, as well as in the FCMM. All components share the same functionality of orienting the pencil and removing wood. Here's our before and after. Our sharpening main body was split into two parts from one. This allows us to remove the fasteners holding the blade, as well as allows the blade to be assembled vertically according to DFA 2 or DFA 12. The retaining washer and the spring was added chamfers for easier insertion of the spring, as well as increased symmetry according to DFA 6. This allows decreased handling time. Our spring was also had closed ends now, This is according to DF8 to avoid tangling and decreases our handling time. Here's our before and after of our handling insertion cost analysis. So overall, we eliminated the fasteners. The blade is now inserted vertically. Our retaining washer is alpha symmetric, so there's no end-over-end orientation needed. And our spring does not tangle. Overall, our product does not change to overall product function. And here is sort of the summary of our impacts.
I will now discuss the process selection for two of our parts. These two parts include the blade and the sharpener lower body, and I've included the critical dimensions on this slide. The blade has its length as a critical dimension, which ensures that the correct amount of wood and graphite are removed with a tolerance of plus or minus 0.25 millimeters. The sharpener lower body also has length as a critical dimension to ensure the sharpener operates in a quiet manner. The tolerance on this part is plus or minus 0.2 millimeters to ensure a secure press fit. Here is a chart which lists the various processes as well as the different criteria for each of these processes. For the blade, we have decided to go with sheet metal working as it satisfies all of the different categories for this manufacturing process out of stainless steel. The sharpener lower body will be injection molded due to its shape as well as the large economic batch size, and the blade will be sheet metal work due to the 2D shape as well as its large economic batch size. The blade will be stainless steel due to its strength and corrosion resistance, and that will be ground and polished to achieve a sharp blade.
We then redesigned these parts for manufacturability. First, the blade, before redesign, required blanking because of the notch. It had a high material cost per part, being 1.9 cents, and the total cost was about 6.5 cents. DfM Pro didn't give us any suggestions for how to redesign, but using DFSM 8 and 5, we put a standard, relatively large hole in the blade, and then remove the notch so it could be part off instead of blanked. This reduced the material cost per part, but ultimately increased total cost to 8 cents per part. Post DFM, because this part was made of sheet metal, we could use hubs to generate an estimate. The hubs estimates were about 4 times less than our analytical estimates, and you can see a drawing of the blade with critical dimensions below.
The other part we did DFM work on was the sharpener lower body. Following the DFA of the part, we analyzed and estimated the total cost for manufacturing given that the part would be produced using injection molding. This resulted in a total manufacturing cost estimation of 54 cents per part. After this estimation, we redesigned the part for injection molding utilizing DfM Pro software for ideas and identifying weak points. This resulted in a new modified design that accommodated recommendations for injection molding. It retains all critical dimensions. Given these changes, we re-estimated the total cost of manufacturing for the part, which resulted in a total manufacturing cost estimation of 64 cents per part. These changes have negligible impact on product functionality, but might lead to slightly negative impacts on assembly costs due to eliminations of a few locating features.
So our design of product service system is a service to resend the blade or the entire sharpener into the manufacturing to replace or resharpen the blade depending on the condition. So for our primary customers, they'll send the sharpener directly to manufacturer. The benefit to the customer is a reduction in cost from buying new sharpeners. In high volume scenarios, typically they'll throw away the sharpeners. This allows them to actually increase the service life of these sharpeners. The benefit to the environment is a reduction in pencil sharpeners that are thrown away due to the dull blades, as well as increasing life of the sharpener. Our secondary customer invariant will also be the exact same, where they can they can either replace the blades at home or send the sharpener to the manufacturer to replace. And the benefits to both the consumer and the environment are the exact same.
In conclusion, our design for manufacturing has led to an ease in manufacturing and the capability for production at high volumes. Some pros of this design include improved assembly processes, while some cons are the limited cost reduction. In reflection, we have a bigger view of impact when making changes, and we have learned to focus on high-cost parts. Thank you for attending our presentation.